So here's an introduction to system of differential equations. Let's say you have two functions, y1 and y2, whose derivatives are individually y1 plus y2, actually 2y2, and then 4y1 plus 3y2. My goal today is to explain to you how to solve this type of differential equations. You can think of this as a constant coefficient homogeneous, because there's no function of x explicitly by itself, right? So it's constant coefficient homogeneous first order differential equation. So it's like if you think about the following, y double prime minus 3y prime plus 2y equals to 0. If you think about this differential equation, this was the easiest second order differential equation type that we could solve, because it had 0. There was no explicit function of x on the right, so it was called homogeneous. All the coefficients are constant, so it told us that the solution looks like e to the something times t. Remember that, right? Yeah. So in the same way, this is like the simplest type of differential equations you can think about. Now, the way we are going to solve these system of differential equation is by making use of matrices. So the first thing that you have to know how to do, you have to know in order to solve such questions, is to change this into a matrix form. And the matrix form of this is the following: y1, y2 differentiated is equal to coefficient matrix. It's 1, 2, 4, 3. Those are the coefficients, right? And this is y1, y2. Now, why is this same as this? Then I have to explain before I do anything else. So let me try to give you a quick review of how to multiply matrices. You learned how to multiply matrices in Calculus 3, right? How do you multiply this? Across and down, right? Across, down. And you're doing dot products. So 1 gets multiplied to y1, 2 gets multiplied to y2, right? And you add them, just like how you do dot products. Okay? So the result of across down to the top one will give you 1 times y1 plus 2 times y2. And then you do the same thing to the bottom one. You do across down, and that's 4 times y1, 3 times y2, and you have to add them. So you get 4 times y1 plus 3 times y2, and that's the resulting matrix. Okay? You call this 2 by 2 matrix. This is called 2 by 1 matrix because it has 2 rows and 1 column. Right? This is also it has 2 rows and 1 column, so it's a 2 by 1 table. It's a 2 by 1 matrix. Okay? And since you're saying that this matrix is same as this matrix, by the way, this is another way of just writing down y1 prime and y2 prime. Right? So if you have this single equation in the middle, what you're really saying is that you're saying that this matrix is same as this matrix. And if you have 2 matrices and you're saying that they're equal, that means every element is equal to each other, right? So saying that these 2 are equal means that the first element should be same as the first element. And look at what we have then. If I say y1 prime is y1 plus 2y2, what's that? That's exactly this equation, isn't it? Right? If I say y2 prime is same as the second element here, what's that? That's exactly this equation. y2 prime is equal to 4y1 plus 3y2, exactly same as this one. Right? So after understanding how matrices are multiplied, then you do understand that this matrix form of the differential equation is indeed same as the given differential equation. Okay? Now, the next question is, how do matrices help us in determining the solution? Well, I'm going to tell you something very interesting about this matrix, the coefficient matrix 1, 2, 4, 1, 2, 4, 3. Okay? It satisfies the following property. So if I have 1, 2, 4, 3, I had to figure this out beforehand, but I realized that if I multiply to this matrix 1 and negative 1, let's try to compute what we get. Okay? So I'll cross down. What do I get? 1 times 1 plus 2 times negative 1. What's that? Negative 1. Thank you. What about this? This times this. 4 times 1, 3 times negative 1. It's positive 1. Right? We can see that this is same as negative 1 times 1 negative 1. Oh, by the way, if you just have a single column, this one is called a column vector, because it's as if it works like vectors. Okay, so you can think of like scalar multiplication. So if you have a scalar to multiply this vector, how do you multiply a scalar to a vector? You just multiply to each element, right? And you do see that negative 1 times 1 gives you negative 1, and negative 1 times negative 1 gives you 1. That's right? Okay, so I see that there's this relation that happens. So magically, why am I saying this is magic? Look, I have this vector 1 comma negative 1. Multiplying this matrix to this vector, column vector, has the same effect as just multiplying negative 1 to this vector. Isn't that amazing? Usually it doesn't happen that way, but for this specific vector, it happens. Okay? Here's another nice vector that's associated to this matrix. You can choose 1 and 2. If I multiply 1, 2, let's see, what's a cross down? 1 times 1, 2 times 2, what do you get? 5, right? If you add them up, you get 5. Okay? 4 times 1, 3 times 2, add them up, you get 10. Okay? Now, do you see that this is just 5 times 1, 2? Is that right? Okay. So I have this relation. So somehow for this vector 1 and 2, this matrix has the effect of multiplying by 5. Now, we're going to call this type of vector as an eigenvector of this matrix, and this number here will be called an eigenvalue of the matrix. Okay? But I'm going to tell you how to get these vectors and coefficients later. For the moment, let's just say that we somehow figure these two vectors and two numbers out. Okay? Now, how is it going to help us? That's actually the thing that I want to show you. Okay? Here's how we want to do this. See, if you think about e to the negative 1t, that has an interesting property. This prime gives you negative 1 times e to the negative 1t. Right? So think about the following case. If I have y1 and y2 equal to, it's 1 and negative 1, so let's say 1 times e to the negative t and negative 1 times e to the negative t. And let's say we plug this into left and right. So, look, this is same as saying I'm trying to take 1, negative 1, and I want to multiply e to the negative t. Same thing, right? This is scalar multiplication, so it's the same thing. If I plug this on the left side, what do I get? This is differentiation by t, So if you differentiate this, the same as just differentiating this and multiplying to this matrix, right? So what am I getting? 1, -1 is just a constant multiple, so it's not going to change, but e to the negative t will differentiate to give you -1 times e to the negative t, right? So you have -1 e to the negative t. Right? That's what you're going to get on the left side. Are you following me? Or if you don't, then there's no point in doing this exercise. Are you getting this? What am I getting if I differentiate?
Over there.
Huh?
You kind of lost me like when you started putting in e to the negative t.
Yeah, so just for a moment, let's just say this is same as this.
Okay.
Which is same as saying this. Okay. Now look at this as some constant times a function. Then when you differentiate, this just stays as it is. You don't change anything. You're just differentiating this, right?
Mm-hmm.
We all know what the derivative of e to the negative t is. It's this one, right? So I just put the -1 in front.
Oh, okay.
Yeah, that's all I did. Okay. All right. Now, if I replace this one again by this, let's see what we get. 1, 2, 4, 3. 1, -1, e to the negative t. Okay. And the question is this true? Asking whether this is a solution to this system is asking whether if I plug in the left side and if I plug in the right side, does this equation hold? That's basically the question, right? But look, isn't this exactly what we figured out over here? Right? It's exactly the same thing, right? See, this one is over here. E to the negative t, e to the negative t is exactly the same. And this is exactly this one, right? So that shows us that if we have such a pair of an eigenvector and an eigenvalue, I can just take that eigenvalue, place it in the E, and just plug it in, and it'll work. It works like magic. Okay. So now tell me what will be the other type of solution? If I use this to make up a solution, what should the solution look like? 1, 2, take the eigenvector, and e to the what? 5t. If I plug this on the left side, 5 will come in front. Right? If I plug in the right side, it's going to look like exactly this vector. So it's going to work. Okay? And then what it boils down to is that, look, we had a system of first-order equations with two unknown functions, and we have found one solution, another solution. What would I do to get the general solution? In general, what should I do? Take C1 times the first one plus C2 times the second one. And this is going to satisfy the differential equation. I'm just taking the linear combination of the two, and that's the solution of the differential equation. So hopefully, although you may not have followed all the reasoning, hopefully you kind of saw that finding the eigenvectors and eigenvalues is critical to finding the solution of this differential equation. If you find them, then you just come up with eigenvector times eigenvalue and write them down. That's it. That's how you solve it. Okay? That's the general scheme of things. So now after this, I'm going to show you how to find the eigenvectors, eigenvalues, and I'll show you the method later.